Welcome everyone to the Vision in Medical session. My name is Leonid Karlinsky. I'll be the chairman of the session. I come from IBM Research, and before we begin, I would like to say a couple of words about what we do in IBM Research in Israel. So besides working on various cool topics in computer vision, machine learning, and augmented reality, we also do some work on medical imaging. In particular, we develop an advisory application for radiologists for detecting breast cancer in various modalities such as ultrasound, mammography, and MRI. So I would like to introduce our first speaker, who is Mrs. Goldman Aslan. She's a co-founder and CEO of DA Imaging Analysis. Mrs. Goldman Aslan has previously founded several startups in the biomed and security industry, where she served as a managing director. So without further ado, I would like to introduce Mrs. Goldman Aslan to talk about auto image processing and machine learning in ultrasound. Welcome.
Stairs. Okay. So thank you very much for coming and wanting to hear all kinds of innovation in medical imaging. My name is Ila, and I'm the CEO and co-founder of DIA. DIA is a software company. We started as an incubator company in the south of Israel, in Ofakim, and it was 7 years ago. And following finishing the incubator period, we were able to create image processing, also using machine learning technology, and implement it in ultrasound. So today I'm going to tell you a little bit about the challenges that we are facing and faced until now when trying to implement image processing and machine learning in ultrasound. So as you may know, there are all kinds of medical images. There are MRI and CT and X-ray and ultrasound, of course. And the common thing about all those modalities is that the number of medical imaging and procedures is increasing significantly from year to year. And one of the main reasons is that the population in the world is getting older. And most of the medical images that we are facing and we are being referred to are related to diseases. And a lot of the diseases coming in late stage in life. So when the population is getting older, more medical images are being produced. Another common thing about all those modalities is that most of the evaluation is being done by visual estimation, which means by just looking at the images and giving the report. Or either in manual ways like marking on the screen. Some of you probably saw that the physician marking all kinds of things on the screen to measure things. So in both cases, it's very subjective and depends on the user years of practice. So when the population getting older, more images are being produced, a lot of the information being performed by visual estimation, and not enough physicians to look at all those images. There is a great need for automated, quick, and accurate tools to help them evaluate what they're seeing on the screen in the various modalities. So we at DIA invented a new image processing technology that is based on advanced pattern recognition and machine learning algorithm, and created fully automated tools to evaluate medical images. What we are doing is we're trying to imitate the way the human eye identified borders and motion, and to do it fully automatically. So our focus is ultrasound. And why ultrasound? So ultrasound doesn't have radiation like CT, so you can do it as much as you like with no harm. And it's not expensive as MRI. And the revolution in ultrasound during the last decade is that a decade ago, the big ultrasound machine cost $200,000, and today it is about half of it. And also the quality of the image got better with time. So having this modality accessible and usable in almost every section of disease or any, if you broke your leg even, or if you have some kind of condition, to able not to send the person to CT or MRI, and having ultrasound as an option is a great option. It's a great, for us, great opportunity. Another thing that happened in ultrasound, that suddenly those kind of devices appeared, which are very small handheld ultrasound devices that cost around $10,000. And the vision of the ultrasound manufacturers is that eventually every physician will carry such a device in his pocket. But again, still most of the evaluation is being done by visual estimation. So doesn't matter how many physicians will carry that, they still need those automated tools to help them evaluate what they're seeing on the screen. So in DIA, we developed this technology, and the core technology can be used to various areas, which means it doesn't only can work on specific organ or specific area, but we started with cardiac ultrasound. And one of the reasons is because it's a very big market, and about 30 million procedures of cardiac ultrasound, also called echocardiography examination, or echo, is being performed only in the United States, not taking into account all those images being used and being evaluated with point-of-care ultrasound or the handheld ultrasound that until now, not all of them are being recorded. So the numbers is even higher than the numbers that I'm just showing on the screen. So this is how ultrasound of the heart, cardiac ultrasound looks like. This is the big machine, and it's very similar to the ultrasound being done during pregnancy, where you have the transducer, and you take in the images from different areas on the chest. But the big difference with cardiac ultrasound that the heart is moving. And compared to other areas that are static, it's very difficult and very important to look at various areas inside the heart, not only one area. So we're actually, in our company, we look at the heart like a bunch of organs connected together, because the left ventricle is not the same as the right ventricle, and all part of it, each part of it is very different. So during the procedure, that if you are being referred to a full echo examination, so first of all, the technician is the one that you are meeting. And the technician usually is taking between 80 to 60 clips of the heart on a single patient, which means this is a lot of data, mostly video clips, from different areas on the chest. And all this data is being saved on your file in the healthcare IT system in the medical center, either inside the hospital or on the cloud. And then the physician opens these examinations from a reading room usually, or even remotely, and going through all those 60 to 80 clips of the heart, each by each, and think of how much time it takes, and everything, and almost everything happening by subjective evaluation, by just looking at the images and writing the reports. So during the last few years, a new area in ultrasound emerged that's called point-of-care ultrasound, that suddenly emergency room, intensive care, remote medical facilities, ambulances, and even family physician in some places in Europe starting to use portable ultrasound devices, handheld ultrasound devices. And over there, even the situation is even worse, because those physicians are not used to use ultrasound on a daily basis, like the ones on the echo labs or the ultrasound divisions, and they have limited knowledge and experience of how to evaluate the heart when using those kinds of devices. So again, the gap between having a great technology but not able to evaluate those images exists in ultrasound in all kinds of segments. So what we did is we created those set of tools that we already got FDA and CE approval for them, for the cardiac ultrasound segment. And we got, and we have a few challenges. The major challenges that we are facing and faced through all the process is that the quality of the image. There are different modalities, different ultrasound devices. Some are high-end, some are low-end, all kinds of images coming out of those devices, and it's very difficult to provide automated tools when you have to deal with various quality of an image. This was the first thing. The second thing is the movement. Everything is moving. It's not static, and the movement is not through one direction. If you look at the heart, it's like moving and doing some kind of a twist. So also the challenge to see and to understand the movement of the heart and adjust our automated software tools to work on that environment. The third thing, and it's very important, is the acquisition, which means with CT and MRI, you are positioning the patient and taking the image. With ultrasound, it's the other way around. The physician has to put the transducer on the body of the patient and find the right view. And again, this is subjectively doing it. You are trying to get the right view as you think it is, but we see a lot of variability between physician and sonographer taking those images. And in a lot of the cases, it's pretty good. And pretty good, we have to challenge and we have to give result also when it's pretty good and not very good. So those are the three main challenges that we see in ultrasound, specifically in cardiac ultrasound, but you can think of it in any area in ultrasound that you have to adjust the transducer. So this is one example that I will show you of one of our FDA and CE approved tools that's called the ejection fraction, automated ejection fraction. Ejection fraction is the percentage of blood coming out of the left ventricle in each beat. The big black area that you see, this is the left ventricle. This is a mirror vision. And this is the pump of the heart. And when the left ventricle filled with blood and doing the contraction, you want to know how strong it is so to take out the blood from the left ventricle to the rest of the body. If it's above 55%, it's normal. If it's below that, there is 3 different levels with different treatments. It can be medicine, it can be interventional. So it's very important to understand what is the ejection fraction, both at the echo labs and at point of care. This is a major indication of the performance. So what they're doing usually, they are looking at the images, at the video clips from different views, and estimating according to their expertise and years of practice. And they say, okay, it's 57, it's 47, it's 35. If they want to have it quantified, what they are doing, they are running the clip, stopping it when they think that the left ventricle is the smallest, and then doing and marking the inner border of the left ventricle, taking this specific frame, put it on the side, running again the clip, stopping when the left ventricle is the biggest, doing again the marking, and put it on the side. Again, doing it from a 2-chamber view, a different view. Again, they're getting into 4 only frames marked subjectively, chosen subjectively, and then there is a formula that gives you the ejection fraction. Having that said, you understand that it's time-consuming. It's not accurate because you get in specific frames, not all the heart cycle, not different beats, maybe one beat not acting the same as in another beat. And what we did is did all this procedure fully automatically, and I will show you. So this is before, and once you press one click, this is after. So what you saw right now, that immediately, and this is the time it takes, within 2 seconds, we mark the inner border of the left ventricle from the both views, track it all over all frames of the clip, all the bits of the clips that there is, give a lot of information about the ejection fraction in each view, the biplane, volume curves, also the possibility to change if the physician don't think that this is the right marking. And again, a lot of information in seconds. And this is what we are doing. So here is an example of a very bad quality of an image. And this is just to give you the sense of the challenges that we are facing. So it's bad in 2 ways. First, the way that it was taken. You don't see a very nice 4-chamber view. There is missing parts, but I will not get into the clinical so deeply. And also the quality of the image, which means it's not that bright, it's not that nice, and probably not from, as I see, not from the high-end devices. So this is one of the challenges. So here you can see how we were able to address this. That's before, that's after. Again, able to do the marking, do the tracking, and give the results. So let's talk a little bit about the data. So how did we handle the data? How much data did we need in order to do that? So in a single clip, like a clip for ejection fraction, for example, there is between 50 to 100 frames. And this is the amount of data that we are receiving from each clip. We have thousands of clips already in our database. We started with few hundreds, but when you multiply them with the numbers of frames, this is a lot of data that we are working in order to adjust and in order to improve our technology. Basically, for the clinical trial, in order to get the FDA approval, we took the amount of data that needed in order to get the FDA approval, and took it to 3 medical centers, one of them in the United States, asked for the most expert physicians and most expert sonographer to do the eyeballing and also the manual marking, did an average between them and compare it to what we can do with our technology. And the correlation was amazing. It was above 90%. And that's actually what we tried to say in this study, that we are as good as the expert. And once we are good as the expert, we can rely on what we are providing. And now it's few more examples of other areas in the heart. This is the segmental wall motion, different views. Again, one click and giving the results. In this case, we also applied machine learning in order. This is the left ventricle has 17 segments, muscle segments, and sometimes the global function of the ejection fraction is okay. It's above 55, but specific area is not working so good, and you have to detect it. So in a click of a mouse, we can also identify the segmental wall motion and the 17 muscle segment. This is also one additional example of before and after. Again, also referring strain, also the referring to the segmental left ventricle evaluation. Another example that you can see here is contrast. Sometimes the echo is being done with contrast, and contrast is very noisy area. And yet we are able to overcome it and provide those automated tools. And this is a new tool that we are going to present to the market this year for the right ventricle and give it assessment also in this area and not only the left ventricle. So basically, I mentioned the challenges that we are addressing. I also want to address another challenge that we're facing, is that we want to be part of the workflow, which means we want to be part of the device itself, or as part of the healthcare IT system. Wherever there is a viewer, we need to be part of those 5, 15, 20 minutes that the physician is doing the evaluation. Therefore, we need to work on low memory and processing power of the device itself, specifically with the handheld device and portable ones that are very low in resources. So here you can see one example of our automated tools being implemented in a handheld ultrasound device. This is Tala, one of our employees that volunteered to pose. So now we are taking the image, pressing freeze, one click, and in 3 seconds, 1, 2, 3, you're getting the results immediately. The ejection fraction. And think on all the situation that this kind of application can help in all kinds of critical situation or even monitoring situation. So this is also a challenge that we address. So our big vision is to be, to expand to other areas and to address all needs in ultrasound, that you put the transducer and when you want to get immediately some kind of indication of what is the condition of the patient. We are already signing agreements with companies like GE and USoft and SUI, and also from the healthcare IT companies. We are also hiring. I know this is the right platform to mention that, so please send us if you were looking for a job. We are looking for engineers. And this was Dia in a nutshell and the challenges that we are facing with ultrasound. Thank you very much.
Well, thank you. Before we go, any questions?
Oh, sorry.
Please come back.
We are short in time, so yeah.
Yeah, it's okay.
I'm sorry.
So, who wants to ask?
Yes. Can you please tell us a little bit about what is under the hood? That is to say, what networks are you using, what training, how do you do the training, a little bit about technicalities underneath?
So I'm sorry, but I cannot refer to this area of questions at this stage. But we are using some. Yeah. Any other questions? No? I don't hear you. No, only a software company. Okay, so tell me.
Okay, thank you. Wait a second.